Good morning. Buenos dias. Hola. Hola. Gonna wait for a couple more people to join us. I'm enjoying this nice, cool morning. Ooh, I should open the window. Get some fresh air. All right, it looks like no one else is coming. So I will begin. Good morning. I hope everyone's doing well. Mr. P here. We are done with forces. Okay, so we talked about Newton's laws of motion. Then we talked about some of the different types of forces that you can consider. Then we did some problems where the forces were diagonal. And then, so two-dimensional force problems. That was the third lesson with forces applied at an angle or an inclined plane, that sort of thing. And then we learned about interacting systems. For our last lesson. So in particular, the Atwood machine, the pulley, all of those things. Okay? So now we're going to talk about energy. Okay? So energy is our next topic. And energy is really useful. So energy is basically a number that tells you what can or cannot happen. Okay? So, if you have enough energy, you can do it. If you don't have enough energy, you can't do it. So it's a really useful concept. Okay. So there are a couple of different types of energy. So one type of energy is called kinetic energy. Okay. And kinetic energy is the energy of motion. zoom in a little bit. The energy of motion. So anything that is moving has kinetic energy. The formula for kinetic energy is denoted by K, and the formula is 1/2 times the mass times the velocity squared. Notice that the velocity is squared, and so that means that it doesn't matter which direction the object is headed in. Because if it had a negative velocity, that negative velocity would get squared and become a positive. Okay, so the kinetic energy is always greater than or equal to 0. The only way to have 0 kinetic energy is to be at rest. Okay, the faster you're going, the more kinetic energy you have. The more massive you are, the more kinetic energy you have. So this is why it's the energy of motion. Okay. So that's one type of energy. Another type of energy is called gravitational potential energy. So anytime you see this word potential energy, potential means an energy you have because of location. So location, all right, is what gives you potential energy, where you are, or what configuration you're in is potential energy. Okay? So gravitational potential energy has to do with how much energy do you have because of your location in a gravitational field. Okay? So generally speaking, the higher up something is, the more gravitational potential energy it has. Because if think about, for example, dams. Dams are like hydroelectric power plants that have dams. They are utilizing the gravitational potential energy of all of that water that's lifted up high on one side of the dam, and then the water drops so that gravitational potential energy is lost, and it comes out on the other side of the dam, and that gravitational potential energy is converted into other forms. So the formula for gravitational potential energy, so potential energies are usually denoted by U, and there are multiple different types of potential energy. So I'll call it U sub G for gravity, and the formula is mgy. Mass times gravity times y, where y is your elevation. So the more you lift something up, the more gravitational potential energy the thing has. Okay? If you move something side to side, you're not increasing its elevation, and so therefore the gravitational potential energy is not changing, so it's a lateral move. If you move something up, gravitational potential energy does change. Okay? Another type of potential energy is called elastic potential energy. Okay. Elastic potential energy is the energy that is stored in an elastic band. Okay. So if you take an elastic band and you stretch it, and then you let it go and it snaps, it goes whoosh, like that, you're releasing the elastic potential energy. So because it's a potential energy, I will denote it by U, okay? And because it's elastic, I will denote it by U sub E. And the elastic potential energy is 1/2 times K, which, if you recall, is the stiffness, times the extension squared. All right? So the more you stretch it and the stiffer the band, the greater the potential energy. One thing I want to be really clear about, though, is, one thing I want to be really clear about is that force and energy are not the same thing. So, for example, the elastic force formula is Kx. The formula for elastic potential energy is 1/2 Kx squared. These are different things, okay? A lot of times students will confuse them. So, force is the more fundamental concept, okay? Forces tell you in detail how things happen. It tells you where things are at a certain time, right? Because it tells you the acceleration. So you know when everything is going to be at a certain location, okay? Energy energy is, hang on a second. Yeah, I know you can't see the whole paper. I'm just zooming in, so the part that you can see is easier to see. I will try to move the paper around. Energy is looking at the motion in a more holistic manner. So energy tells you, can something happen? It doesn't necessarily tell you the details. When is it going to happen? Or how much time is it going to take? Or whatever. It just tells you, can it happen or can it not happen? All right? And if it does happen, what's going to be the result? But it's not going to tell you the whole process. To understand the whole process, you need forces. So forces are the most detailed description of what's happening. Energy is a holistic. Okay? So, as you might expect, forces are much more difficult than energy. Okay? Because forces are trying to answer a much more detailed picture. So it's more complicated to think in terms of forces. So if you don't need 100% knowledge of what's going to happen, if you only need to know, can this happen or not, energy is where you want to go. All right. So energy is really useful because it's easier than forces. Energy is easier to work with. And oftentimes it gives you the answer that you need. Okay? So we have these three forms of energy. There are some other forms of energy that that are important. By far, the most important additional form of energy is what's known as internal energy, also known as heat. IB is really particular, though, that they want you to call it internal energy. So I'm calling it internal energy. And so what is heat? If something is hot, what does that mean? It means that the atoms are, so if we look at something at the microscopic level, it's made of atoms, and those atoms are bouncing around randomly, and the energy of that random bouncing around of atoms is internal energy. So if you touch something and you get burned, if I touch the camera and it burns me, what's happening is that the atoms in my finger are coming in contact with the atoms in the camera, and because the atoms in the camera are so hot, they're bouncing around so vigorously, they bounce into the atoms in my fingers, and it actually destroys chemical bonds and things like that, and I get hurt. Okay? So internal energy is just the random motion of atoms within a material. Okay? You can also have things like chemical potential energy. So chemical potential energy is the energy that is in gasoline, the energy that is in food. We consume chemical potential energy. Okay. There's, of course, electrical energy. So these are just a few examples. The total mechanical energy of an object so the total mechanical energy, I'm going to say actually of a system, is denoted just by capital E, and it's equal to the kinetic energy plus all the different types of potential energies, okay? And this kinetic energy, when I say that, I mean the total kinetic energy, so adding the kinetic energy of all the objects in the system and the potential energy of all the objects in the system, okay? So that's called the total mechanical energy of the system. All right? So let me box these in. Now, all right. So there's a really important law. It's called the law of conservation of energy. So in physics, we use this term a lot, conservation law. Okay? And what a conservation law is it's a statement about how the total amount of something is not changing as time goes on. So this means total amount isn't changing. Okay? So if I say, so there are a number of conservation laws in science, right? Conservation of mass. The total amount of mass is not changing. Conservation of electric charge. The total amount of electric charge is not changing. Conservation of energy says that the total amount of energy is constant. So the initial amount of energy that you have is equal to the final amount. Okay? The initial amount is equal to the final amount. Where each of these E's is given by this equation. Okay? Now we have to be a little bit careful here because this is the total mechanical energy. So mechanical energy refers to basically forms of energy that are tangible. Heat is sort of an intangible form of energy. So if we just talk about the total energy is a little bit different. The total energy is basically mechanical energy plus heat. Okay, so yeah, that's kind of an important distinction. All right, or total mechanical energy plus internal energy. We're going to talk more about that in coming lectures. So another way of stating the law of conservation of energy is that energy cannot be created or destroyed. Okay? Only transformed. So, for example, if we look at the energy of a system, it's kinetic plus potential. And I'll consider the total amount of total energy, not just mechanical energy. So maybe I'll include the internal energy, which is denoted by Q. Okay, so Q is heat energy. So what if the the total amount of potential energy goes down? Now, if energy cannot be created or destroyed, only transformed, all three of these terms have to add to a constant, no matter what. Okay? So if one form goes down, the other forms have to compensate by increasing. Okay? So energy is transforming, it's shifting around from one form to another form. All right? So you can actually think a lot about energy as like money, because the money isn't really being created or destroyed, but it's being passed around between people. Okay? The total amount stays the same. That's an analogy. It's not a perfect analogy. So, some people attach sort of a mystical significance to energy that kind of like it's this miraculous law. But if we think about how was energy discovered, if we think about it as something that actually exists, how was energy discovered? Basically, what physicists did is they were like, is there a quantity that doesn't change? Okay, is there a quantity that doesn't change? And they were able to combine variables, and they found that when you combine variables in this way, the total amount doesn't change. Okay, so I take a very pragmatic view of energy in that it's simply a function. Energy is a function of all the variables in the universe that is constant. It is possible. So really the significant thing is that there exists an energy function. It is possible to define an energy function that is it's possible to define an energy function that is unchanging as the universe proceeds in time. Okay? So it's just a definition that happens to be, it's like a good definition. I'm getting a little bit philosophical here. Sorry. If we found that the law of conservation of energy was not true, then what physicists will do is they will define a new form of energy to make it true. You get what I'm saying? So you can't beat the conservation of energy. There's no way around it. If you think that you violated the law of conservation of energy, you did not. All you did was discover a previously undefined form of energy. And then physicists will roll that into the definition of energy. Okay? I suppose that I should probably give you the units of energy. Units of energy are called joules. Okay, which is denoted by J. An equivalent unit of energy that you've probably heard of before is the calorie, capital C calorie. And 1 calorie is 4,186 joules. So, have you ever heard, for example, that the recommended diet is 2,000 calories per day? All right. So what they're saying is you should eat 2,000 calories worth of chemical potential energy per day in order to function, to meet your energy needs. All right, so calorie is a unit of energy, but we're going to use almost entirely joules. So I'm sticking with joules. All right, so so let's do an example. The rest of the class is just examples. Let's suppose a 50 kilogram trail runner is running at, let's say, 7 meters per second on top of a 300 meter tall hill. Okay? So here's the hill, and the trail runner is on top of the hill. Okay? And we want to know what is the total energy of that trail runner, total mechanical energy. So we're only gonna include the three forms of energy that I defined on the last page there. Okay, so the energy is going to be the kinetic energy of the trail runner plus the potential energy of the trail runner, which is mgy. And there's no elastic potential energy in this problem because this person is not a rubber band or a spring or something like that. So these are the forms of energy that they have. So now I just plug in. So I have 1/2 times 50 times 7 squared. And then I have plus 50 times y, which is 10 times 300. Plug that into the calculator. So 1,225 joules of kinetic energy. And 150,000 joules of potential energy. So in this case, the potential energy far outweighs the kinetic energy. That's okay. So it's about 151,225 joules, which we could abbreviate that as 151 kilojoules. Okay? So that's the total mechanical energy of the trail runner. Let's go to page 2. All right. So we're going to do some more examples with conservation of energy. Okay? So best example of is a question, what is y equal? Y is elevation. Elevation. All right? I'm in the algorithm. Yep. Hello, Morgan. Nice to have you drop by. So a good example is a roller coaster. This is a great problem of something that is easy to analyze in terms of energy, but really tough to analyze in terms of forces. So what if we have a roller coaster cart? And here's the path that the roller coaster takes. Okay? So it's a really torturous roller coaster. Okay? And let's suppose that the roller coaster cart starts out right here. Here's the person with their arms up. Are you an arms up person on a roller coaster, or a holding on for dear life person on a roller coaster? I was a hold on for dear life person, and then I must have been like 25 years old. I was like, all right, I must get over my fear. And then now I'm an arms up person. Okay, the roller coaster starts at rest. Okay, and let's say that the roller coaster begins, the cart begins at an elevation of 70 meters. This is a really tall roller coaster. Okay, so what's going to happen is the roller coaster cart's going to go down there. And we want to know, what is the speed of the roller coaster cart when it gets to the bottom of the hill? Okay? So energy is conserved. How do we now, let's think about, how would you solve this in forces? Well, at any point on the roller coaster cart has a normal force, and it has gravity going down. Okay? So it's doing a loop-de-loop. You've got a normal force. You got gravity going down. So it would just be incredibly complicated, because the normal force is basically you're doing loop-de-loops, and the normal force is going around in all different directions. So it's really tough. But if we think about this in terms of energy, it's really simple. It's just the energy here equals the energy there. Okay? So initial energy equals final energy. All right? Initial energy equals final energy. So what form parenthesis S do you have to start? Well, the roller coaster starts at rest. Okay? So that means that it does not have any kinetic energy, because kinetic energy is the energy of motion. Okay? But it is elevated. It has a high elevation. So it has gravitational potential energy. Elastic potential energy is not relevant to this problem, because we're not talking about elastic bands. Okay? So you start out with gravitational potential energy. Okay? The roller coaster cart goes woo. Okay? And then now it goes to the bottom. So it loses all of that elevation. So the y value becomes 0. Okay? And so we still don't have elastic energy, so we must have kinetic energy at the bottom. Now, some of you might have been thinking, what was the mass of the roller coaster cart? And it turns out that that's not relevant in this case. Okay? The reason that that's not relevant is because m is on both sides of the equation, and so it cancels out. Okay? So the roller coaster is on Earth, so gravity is 10. The elevation is 70. That equals 1/2 v squared. So that says, solving this equation says that v equals square root of 1400. Which is 37.4 meters per second. Okay? So this is the power of energy, you guys. This is the power of energy, because we didn't have to worry about the detailed shape of this roller coaster track. Okay? If we analyzed it in terms of forces, we would have to know all of the details. But it's just energy is a holistic approach to physics. We're saying this is where you start, this is where you end. Let's look at the energy where you start. It's got to be equal to the energy where you end up. Doesn't matter what happened in between. Okay? So it's very powerful in that way. Let's do another example. Let's say you are launching a slingshot. Okay? Wow, that's a really good drawing of a person with a slingshot. I have to say. So there's so this slingshot has a stiffness of, so the K value of this slingshot is let's say 111 or 110 newtons per meter. Okay. The mass of the stone that the person is launching is, let's say, 0.03 kilograms. Okay, so I gave you the mass this time, and you'll see why in a second. And the person pulled back the elastic band by, let's say, well, if I'm like that, using a rubber band, basically you can pull it back by your wingspan, whatever your wingspan is. So, let's say maybe 0.8 meters. Okay? And we want to know, what is the launch speed of the pebble? I need to go get another slingshot. I used to have a wrist rocket. If you've ever heard of a wrist rocket before, it's like it's a slingshot, but it braces on your arm so that you can pull back the elastic band like really, really far. They're kind of fun. If you have a sibling, it's a fun thing to do with a sibling. Just go get a slingshot and, I don't know, shoot some cans with pebbles. That's what me and my brother like to do, or one of the things that we like to do. Okay, so energy is conserved in this case. All right. And so we're going to assume that while the pebble is being launched, it stays at the same elevation. Okay. It stays at the same elevation the entire time. So we'll just call that elevation y equals 0. Now, here's the beautiful thing about gravitational potential energy. You have the ability to choose where y equals 0 is. Okay? So in this problem, I chose y equals 0 to be the lowest point, the lowest place that the roller coaster goes to. Okay? For this problem, we are assuming that y equals 0 is wherever the pebble is, whatever elevation the pebble has. So because we chose y equals 0 to be there, there's no gravitational potential energy in this problem. Okay? The pebble starts at rest. So what the form of energy that the pebble starts out with is elastic potential energy. Okay? And then that elastic potential energy becomes, as the rubber band relaxes, it becomes kinetic energy. So my final energy is kinetic energy. All right? So you can see why I had to give you the mass in this problem, because there's not mass on both sides in in this problem, mass is on both sides, so it canceled out. In this problem, mass is not on both sides, so I can't cancel out. 1/2 is on both sides, so I will cancel out 1/2. The stiffness is 110. The elastic band is stretched by 0.8 meters. The mass is 0.03. Okay, so I can solve this for the launch speed of the pebble. And then you can do a projectile motion problem. See how it all starts to link together. You have one of the things about physics is you use one tool for part of the problem, then use another tool for so you could use conservation of energy to figure out the launch speed, and then projectile motion to figure out how far it's going to go. All right, so that's pretty nice. So I find that the launch speed is 48 meters per second or so. Okay. So yeah, you can define y equals 0 to be wherever you want. Now I have a question for you. How would this question, this example I did, change if the roller coaster had an initial speed? Type it in the live chat if you know how this problem would change if the roller coaster had an initial speed. Cool. Yeah, you guys get it. Excellent. So initial still equals final, but what I would have is I now have two forms of energy that I'm starting with. So I add both of those on. So 1/2 mv initial squared. Okay. So it doesn't have to be one form of energy becomes one form of energy. It could be two forms of energy become another two forms of energy. It could be, you know what I mean? So you just have to have initial energy equals final energy. All right. You can start out with more than one type. You can end with more than one type. And you just add them all in to either side of the equation. Okay? All right, so I think that's my lesson for today. So I will see you in the Zoom room.